Welcome back to the second part of our lesson on photoelectron spectroscopy and electron configuration. You can see here that I've added the dock cam, so we are going to do some switching around, so just be prepared. The thing that's really interesting about PES diagrams is that this is actually the way that they figure out how electrons are layered within a particular atom. They confirm that we've got these shells that exist that can hold specific numbers of electrons. And honestly, I didn't learn it that way. And I think that it actually makes things make more sense. Like there's some evidence that you just don't have this random, like weird layers of electrons. Like how do you prove that? The PES diagram proves that. So we are going to talk about electron configuration and just brush over that to see if you need any help with that, and then go to orbit diagrams. So if you recall, the PES diagram shows us the different peaks that you end up seeing when you take the different types of electromagnetic radiation and bombard the atoms. And so based on the evidence that they get from those particular electron diagrams, it gives rise to this particular set of orbitals we have here. So we have the 1s, that's the very closest, then the 2s shell, then the 2p, then the 3s shell, then the 3p, the 4s shell. And then if you think about this diagram as down here below the 1s is the nucleus, you end up having a situation where once you get into different types of shells that are further and further away from the nucleus, there's kind of this weird intermingling that happens. So even though there is a 3 in front of this 3D shell, it doesn't mean that you get the 3s shell, then the 3p shell, and then the 3d shell. That's not how this works. What ends up happening is that you have the 3s shell, then the 3p, and then evidence shows us that there's only 2 electrons that show up in the next shell. But then all of a sudden there's 10 electrons in the one after that, and it causes problems. And what they realize is that the different electron shells, even though we give them numbers of 2, 3, 4, whatever, they aren't perfectly layered. You start to get overlapping and intermingling of the layers happening once you start to get up into the third energy level is what we call it. So this 3 here indicates the energy level. So the 4s shell from the 4th energy level actually comes before the 3D shell in terms of its distance from the nucleus as it's empty. So when electrons fill in, what they've figured out is that they fill in closest to the nucleus, and then they keep filling occupied, let me try that one more time. They keep filling empty orbitals until they have no more electrons left. So if they get into a situation where the 3p orbitals are full, instead of going to the 3d, they go to the 4s. Okay. Now, what ends up happening is that our periodic table is organized in a shape that gives us what we call these blocks on the periodic table. And the first 2 columns on your periodic table, or the first 2 groups, form what we call the S block. The middle chunk are transition metals. They form the D block. The P block is the right-hand side of the periodic table, and down at the bottom here, we have the F block. Now, these blocks are the width that they are, if you recall, because of the number of electrons that you can hold in those particular shells. So in the S shell, it can only hold 2 electrons. So we have these 2, this chunk of the periodic table here is 2 columns wide. The D block can hold 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes to represent the D block. The P block here is 6 boxes wide because the P shell can only hold 6 electrons. And the same for the F. The F is 14 because it can hold 14 electrons in the F shell. So when we talk about our electron configurations, what you have to do essentially is you want to find the element that you're looking for. So maybe it's this element here. That would end up being fluorine. And what you want to do is think about ending your electron configuration where fluorine is located, and you need to go through and fill up all of the shells until you hit that fluorine. So what I have to do is I have to put 2 electrons of fluorines into the 1s shell, but I still have electrons left. So then I need to keep going up to the 2s shell, and I'm going to put 2 electrons in there, but I still have 5 more electrons that I need to deal with. So I'm going to put them in the 2p shell, and we'll see what happens. I have 1, 2, 3, 4, 5 electrons, and that gets me into this position here on my periodic table. So my electron configuration is going to be 1s2, 2s2, 2p6, nope, lies, 2p5 for fluorine. So with your electron configuration, if we go back to this slide, you put 2 electrons in each of these positions here as we fill up, and then we go kind of until we run out of room. Okay, so you just keep loading them in until you run out. So in the case of fluorine, we had the 1s, the 2s, and we only had 5 electrons to fill up the 2p, so our electron configuration is 2p5. That is kind of like the address for your electrons. So it lets us know that there's 5 electrons in the outermost shell, that valence that we talked about, and then we have core electrons where there's 2 in the 2s and then 2 in the 1s shell. Okay, so I know that was a really quick example, but what I want you to do now is I'd actually like you to pause and then see if you remember how to do electron configuration. So we have 5 examples that I want you to do. I want you to do carbon, calcium, calcium plus 2, so the calcium positive ion, palladium in the abbreviated version, and then hafnium in the abbreviated version as well. So we are going to pause our video. You're going to give those a try, and then I will go over those answers in just a second. Okay? All right. It's answer time. So we are going to take a look at all of the electron configuration practice and see how things went. So when we start with our first one, we have carbon. Carbon is located here on our periodic table. So when you find it, it's in the second row in the P block right here, okay? And it ends in the 1, 2 in the second box. So it kind of tells you already that your electron configuration is going to end in 2p2. Hopefully that makes sense to you because we've got the P shell second box here. So all we have to do is kind of fill in the electron configuration up until that point. So if you think about starting here in your periodic table, we travel through the S block in the first period, so that's 1s. Then it's the 2s shell, and then we hit the 2p. So my electron configuration is going to be 1s2, 2s2, 2p2 for carbon. Okay? Calcium is the next one. So we are going to find calcium on the periodic table, and we recognize hopefully that this whole first set of columns here, those are our S block, this is our D block, and our P block. We don't have to deal with this F block down at the bottom, but we will, so that's coming. So anyways, with calcium, if we look at it, it ends in the 4s block. So my electron configuration is going to end in the 4s, and then because it's in the second box, 1, 2, my electron configuration is going to end in s2. Okay? So now it's just a matter of filling things in the correct order from the 1s shell all the way to the point where you get the to the 4s shell. So if you think about going through all these, we go through the 1s shell, both boxes, so I'm going to write 1s2. Then it's the 2s shell, we have to go all the way through, so it's 2s2, all the way through this shell, the 2p, through 6 boxes, so it's going to be 2p6, 3s2, the third period here has the 3p shell, so that's the 3p. We go all the way through it, so it's 3p6, and then we end in 4s2. I did not space that well, but that's okay. All right, hopefully that went well for you. The next example that we have is the calcium 2+ ion. Now, if you recall correctly, calcium 2+ means that we have lost 2 electrons. So normally calcium has 20 electrons. Okay. calcium 2 plus only has 18 electrons in it. So since calcium 2 plus has 18 electrons, it has an electron configuration like element number 18, like argon. There is a special name that we call those elements that have the same number of electrons, and it is called isoelectronic. Okay, so again, isoelectronic means that argon and calcium 2 plus have the same number of electrons. Iso means the same, electronic means electrons. So isoelectronic means that they have the same number of electrons. So calcium's electron configuration is going to end up being just like argon's. And if you think about the difference between calcium and argon, it's 2 electrons, and our 4s shell has 2 electrons in it as well. So our electron configuration for this guy is going to be 1s2, 2s2, 2p6, 3s2, and then 3p6, and then that's it. Okay? Alrighty. I'm going to switch to a different note card here. Okay. Our next example is going to be palladium. And if we find palladium on the periodic table, it is number 46. Now, once your electron configurations start to get really big, I recommend writing them in the shorthand notation. And unless they're specific about it, you probably could write things in the shorthand notation. And I'll take that for you, but we have to remember how to do it correctly. So palladium is located here on the periodic table. If I want to write a shorthand electron configuration, what I need to do is back the truck up, beep, 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 back up to the previous period and its noble gas. So if palladium is in period 5, I'm going to go up to period 4 and find its noble gas. And the reason why we use noble gases in these notations is because we know that noble gases have this kind of steady structure to them. They don't really change. They don't really react a lot. And so their electron configurations are pretty stable. So what we're going to do is we're going to write Kr in parentheses. And what the Kr in parentheses does is it tells us that my electron configuration is identical to Kr up until a certain point. So palladium's electron configuration is exactly the same as Kr's, and then we got to do some different stuff. So since I'm in the 5th period here, my next shell that comes after the Kr is going to be 5s2 because it's the 5s shell, and I go through both boxes. Now, if you remember, the the D shells are off by 1. So in the 4th period, this is not the 4D shell with scandium. This is the 3D shell. So down here, that starts with yttrium. This is the start of the 4D shell, not the 5D shell. So my electron configuration is going to be 4D because it's the 4D shell, and then I'm going to count boxes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm over to the 8th box, so my electron configuration is going to end in 4D8. Hopefully that makes sense to you. Remember, you can only use these noble gases for the shorthand. You cannot use anything else. All right, the last one is going to be hafnium, which is HF. Now we're going to write this in shorthand notation because HF is all sorts of at the bottom of the periodic table. It's number 72 here, and so we're going to go over that. Okay, so HF, write it shorthand. If you think about it, back the truck up from hafnium to its noble gas neighbor, and that is going to be xenon. So in brackets, I'm going to write XE. Okay, so I've got XE in brackets. Then I'm going to continue on with my my journey across the periodic table into the 6s shell. Now I need to go all the way through the 6s shell to get to HF, so I'm going to write 6s2 because I go through both boxes. However, there is some funny business that happens here. If you notice, the electron count here, or the atomic number, goes from 57 all of a sudden to 72, and that's because there is a detour that happens down here with these particular elements. They're called your rare earth elements. And what happens is this is a detour through the F shell. They essentially pull these two chunks out because they wouldn't fit in the periodic table. So you have to kind of imagine that you slice them and then you pull them apart. Now my periodic table might look a little bit different than yours as far as the elements that are here. I think yours have La and AC here in this first position. There's actually like a ton of like nerd debate going on about if LA belongs in this box or CE. And this is an older version of the periodic table. And so it's just a little bit different, but I wanted to show you this in color. So back to our electron configuration. I am going to go 6s2, and then instead of going to the 5d shell to get to hafnium, I need to include this shell down here. So in my electron configuration, it's going to be 6s2 and then 4f14, because I go through 14 boxes down here before I get back up on my way to my electron configuration. And then I'm going to finish it off in the D shell here. This is going to be the 5d shell. It's going to be 5d1, d2. Okay, so those are a little bit weird. There's not much we can really do about it. That's just something that we have to deal with. They will ask you questions about that F shell, so make sure that you don't forget that. In the event that you have a noble gas as the thing that you have to write the electron configuration for, you have to go to the previous noble gas and then do the electron configuration. So argons would start with neon, and then you'd go to another one. Okay? Hopefully this makes sense to you. If you find yourself having any questions, we can go over them in a Google Meet, and hopefully we get things cleared up. All right? Good luck.